Okay, so we were just going to make our scatter plot from the table. So I put in the L1 and the L2. Now I'm going to go back to my y equals, and I need to clear out both of these equations. I also want to turn my plot on, so you just arrow up to that plot and hit enter, and then it's dark, so now you know it's on. We're going to want to change our window, so we hit the window button, and our x values go from 0 to 43, so I'm going to do 0 to 50, or 45, whatever you want to do. And then I am going to go, if you look at our y values, they start at 487, go up to 7,000, so I'm going to do 0 to 8,000. And just so that my scale doesn't look crazy, let me go up by 500. That just makes it graph faster. So when I graph that, what I want you to look at is we have this growth rate here that's very exponential, but then we see our growth start to slow down. And as it's slowing down, that's what makes it kind of look more like an S, or a logistic curve. So if we were going to kind of plot our scatter plot, it just says create a scatter plot. What does it look like, and how does it compare to the standard exponential curve? So we can say the growth slows at the end. So what we kind of had was we had exponential, and then it slowed down. And so what that leads me to believe is this is not an exponential function, but it is a logistic function. So instead of doing an exponential regression, we are going to do a logistic regression. So let's go back and look at our calculator again. So I'm going to hit stat again. I'm going to go over to calculate, and I'm going to find a logistic regression. So it's not very high up there. It's actually letter B. So we're going to hit logistic, and then just go ahead. I'm going to store my regression equation because the next part of that problem is actually asking me to graph my function on top of my scatter plot. And so if I store the equation in my y1, then I don't have to plug it in. So it's just kind of saving me some steps. So you hit vars, yvars, so you arrow over to yvars, function, and y1. So you see y1 is shown up in the store regression equation. Now we just arrow down to calculate. Think, 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 think. Maybe I broke it because it's still thinking. Oh, okay. And so they gave us A is 1.06. Now I want you to notice here that our variables here don't line up to the variables that I gave you for a logistic function, because A is actually what's next to the E. So I'm going to go ahead and write this function down on our notes. So the function that I got is, this is P of T equals C 1 plus AE to the negative BX. And that was in the form that they gave it to you. So this is 8629.277. I'm going to round to the third decimal place. 1 plus 106.778 e to negative 0.147x. So I want you to notice that the calculator switches some of the variables around with this formula. Still means the same thing, you just have to know how to interpret it. Now, let's go back to our calculator and look at, so if you go to y equals, look, they put that whole thing in there for you. Isn't that nice? So let's look at what it looks like when the two are graphed side by side. So that's pretty good. What I do notice is that down at the bottom, when the x values are smaller, it doesn't match up quite as nice. We have a much higher value for 1 than what our regression does. However, when we get to the exponential part, it's matching up quite nicely. So this is pretty good. I would say it would match. I would say it matches well. So we are going to say it matches well. Okay, C. Based on the regression equation, what is the carrying capacity for bald eagles? So remember, carrying capacity is actually the asymptote, which is the number on top. So I'm just going to round this, since we're talking about the number of breeding pairs, to 8,629 breeding pairs. And remember, I got that from the numerator. The numerator gives us the carrying capacity. Remember, it's the asymptote, so it's the population that our function is going to approach but never actually touch. That's what an asymptote is. It says the protection of bald eagles will stop when there are 7,500 breeding pairs. So according to our model, when should this happen? So 7,500 is equal to our P of T. So we're going to set that equal to this crazy equation. 7 over. So this looks pretty crazy, but what we're just going to do is multiply by the denominator, right? And so we get 7,500 times 1 plus 106.778 e to the negative 0.147x equals 8629.277. And then we're going to divide by 7,500. Okay. And then I've got this 1 over here, so I'm going to subtract 1, just because that's going to make my life easier. So I have 106.778 e to the negative 0.147x equals 0.15057. And remember, I'm keeping the rest of that in my calculator. Now I can divide by 106. Undo. Is there an undo button here? No. Undo, 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 undo. Well, that didn't help me. Okay. 106.788E. Okay, so we're going to divide by 106.778. And now we have E. So let's put that here. E to negative 0.147. X equals 0.0014, keeping all those decimal places. And now we're going to take the natural log of both sides. So negative 0.147x equals the natural log of 0.0014. And divide by negative 0.147x. Oh, no x. Divide by negative 0.147. And finally, we get x equals 44.65. And that's 44.65 years after 2000, oh, not 2000, after 1962. Because that's when the bald eagle protection started. So 44.65 years after 1962 is during 2006. So during 2006, there were approximately 7,500 breeding pairs of eagles. Once again, sorry I didn't leave you enough room for that. Hopefully you were able to follow along. Let's go ahead and look at example 4. This is our first exponential decay problem. Okay. So exponential decay, the only difference is now we have a negative sign. So K is actually called the decay rate, where K in exponential growth is the growth rate. Okay. In 1970, there were approximately 100,000 cases of polio worldwide, and this number has decayed exponentially at a rate of 50% each year. it says, at what point in time were there half as many cases of polio as there were in 1970? Well, if our initial amount of cases is 100,000, what would half that be? That would be 50,000. And so we know that our decay rate is 50%, so K is 0.5. And now we just need to plug this in and solve for T. So 100,000, equals, oh, I put that in wrong. 100,000 is actually the original, so it's 50,000 equals 100,000 times E to the negative, because we're using this formula, negative 0.5 T. So we're going to divide by 100,000 to get E all by itself. And what you get is 0.5, which makes sense because we want to know when there's half. 0.5 is half. E to the negative 0.5 T. So it does take the natural log of both sides. And then the E just basically cancels out, right? So when we take the natural log, that cancels. And we have negative 0.5 T. And so then we're just going to divide by negative 0.5. So we have the natural log of 0.5 divided by negative 0.5. Now that's just a coincidence because our decay rate was 50%. And when you do that, you get 1.386 years. So very quickly is the number of cases going to be cut in half. Now, I do want to point out that when we're doing half time, it's very similar to the doubling time. We could find T just by taking the natural log of 0.5. So this is a little, we take the natural log of 1/2 or 0.5 and divide that by the K. And think of it as negative because it's negative K. So that's pretty good. It says, do predictions based on this model support the claim that polio has all been eradicated for over 20 years? Over 20 years. Well, 20 years from 2017 minus 20 would be 1997. And so 1997 is how many years after 1970? Well, that's 27 years. 27 years after 1970. So that's the time. So we're going to be putting in 27 for T. And so now that we know T, we can just plug in and solve. So we know we don't know P of T equals 100,000 times E to the negative 0.5 times 27. So we would just go ahead and put that into our calculators. And when I do that, I get, I'm putting it in right now. So I didn't have this one ready because I didn't have the right number. Times 27. And I get P of T equals 0.137. If we were going to round that to the nearest whole number, because we're actually talking about the amount of cases, we would round that to 0. So that is approximately 0 cases. So the question is, does that support the claim that polio has all been eradicated? And the answer is yes. It does. Okay, so that's the end of this video. We have one more video and then we're all done. So I'll see you at video 3.